Okay, well, so so our basic ingredient is this. So let's again use the cubic matrix model as an example. So the basic ingredient is this. So for example, we wanted to join these two vertices. We can do it in this way. And we thought about this as a Riemann surface with genus 0. This is a planar diagram which has 3 boundaries. So it's really a Riemann surface with 3 holes. So this is the first point of view on these double line diagrams as a Riemann surfaces with boundaries, with holes. And the number of closed lines corresponds to the numbers of holes. But there is another point of view which is also very useful, in which we associate double line diagrams to Riemann surface with no holes. And the way to do this is the following. Now, the way to do this is what is called sometimes in physics going to the dual graph. So you can think about this as a graph, and then you can associate a dual graph by taking essentially associating the outgoing edges to orthogonal edges. So this object here can be associated to a triangle. Okay. So you see that so by going to this dual polygon, a trivalent vertex, so a vertex with 3 legs, which is called sometimes trivalent vertex, corresponds to a triangle. Okay. Now, generalize, and if, for example, we have like a tetravalent graph like this, and this will have a dual graph, which is a square. Okay. So this is the way it works. Now, what happens when we want to when we construct diagrams? Well, when we construct diagrams, we have to use Big's theorem and we have to make pairings, right? So let me try to write this diagram. So let me try to, oops. Let me try to use this to. Let me try to illustrate this. So here is a cubic graph. Here is another cubic vertex. Here is another cubic vertex. And now I consider the triangles associated to them. And now the gluing instructions. Remember that the glue instructions tell me that I have to glue this with this, this with this, and this with this. These are gluing instructions now that can be interpreted as gluing instructions for the faces of the triangle. So if you do this, in this case, well, what you will get is some gluing instructions for these triangles. So you have this, and you glue each face with the opposite face in this way. And what you get when you do this is something like this. And topologically, this is a sphere. It's a sphere. It's a sphere made out of gluing 2 triangles. Okay, so it's a very strange sphere, which is what I call sometimes the ravioli sphere, because it looks like a ravioli, but topologically, ravioli, right? So this is what it is, and you can actually represent this in terms of identifications of faces, as in standard topology. So let me show this in this way. So I can try to write, you know, if let me try to make this drawing, which is actually quite instructive. So I have this. Let me write the triangle like this. Let's suppose that I already joined these two lines. So I'm already joining these two things. So let me now write. Oops. Let me now write the triangles. So you see. Well, this is not quite. This is not as good as it should be as a drawing. Let me do it like this first. Okay, so now, okay, well, you get the idea. So when I represent this gluing through gluing of triangles, I'm joining these two sides here, and now the gluing of these two lines and these two lines is an instruction to identify these two faces. Okay, so this is an instruction to identify these two faces. So again, you can see how the ravioli is formed. I glue this face with this face and this way with this face, but this is again a sphere. Okay. Now this representation is actually useful in order to understand what happens when we do the opposite diagram. Remember that there was this diagram in which we crossed the oops, no, sorry. It's always tricky to draw this diagram. So okay. So there was this diagram. So you can see that if we think about this diagram in this way, now we have to do the identifications in a twisted way. So we have to glue this guy to this guy. Let me write it. So we have to glue this guy to this guy and this guy to this guy. Okay. So this is the type of identification which would give you this crossing. But if you do this kind of identification and you forget about all these double lines, what you have here is what? You have a square made out of two triangles, and now you identify this side with this side, and then you identify this side with this side. But of course, when you do this is again, you know, a useful model in topology for Riemann surface. This is exactly how to get a torus. A torus is exactly obtained by taking a square and identifying the opposite sides of the square. This is what gives you a torus. You see, when you glue these two sides, if you glue first these two sides, you get a cylinder. When you glue these two sides, and when you glue these sides together, then you get the torus. Okay, so now so these are examples, but you see that if I represent the diagrams, the double line diagrams through the dual polygons, and obtain now closed Riemann surface without holes. Okay, so this is sometimes people prefer to use this correspondence between diagrams and Riemann surface because it gives you closed Riemann surface on the nose. Okay. Now we can now make the counting. Okay. So we can now do the counting. Remember now. On the counting of power that we were using before in the other model for Riemann surface. So now remember that a double diagram has vertices, edges, and number of closed loops. Now the number of vertices, it's interesting when you go to the dual diagram in terms of triangles, what happens. So the number of vertices corresponds now to the number of faces of the dual diagram. Okay, and you know, this is very easy to see because here you see this vertex. Each vertex is your face in this diagram. So if you think about this, for example, here we have two faces which correspond to the two vertices. So now faces correspond to vertices. Okay, edges correspond to edges. That doesn't change because the edges here, each edge of the original diagram is orthogonal to a line in the dual diagram. So edges are preserved. And the interesting thing is what happens with closed lines. Now, it's very nice to see that, you know, closed lines, actually, what they do is they encircle, they circle vertices of the dual diagram. So you see, for example, this vertex here is going to be glued to this vertex here. And you can see that this closed line, let me do it in the original one. So for example, let's look at here. It's actually clearer here. So, sorry. So when we put these lines together, so if we close here these lines, you see that. Let me throw it again. So, okay. And now let me eliminate this, and let me close these things. So let's look at this vertex. Now, when you glue, this vertex is going to be glued to this vertex. So in the resulting figure, they're going to be identified. And precisely this vertex, which is going to be glued to this vertex, corresponds to this closed line here. Okay. In the same way, this vertex here, or if I continue drawing this diagram here, you can see that these two vertices, which are going to be identified, are associated to this single line here. And finally, this vertex, which is identified with this vertex in the final figure, is going to correspond to the other closed loops. So in this ravioli, you can see that there are three vertices in this ravioli, okay? And these three vertices of the final figure correspond to the three closed loops of the original diagram, okay? So the number of closed loops corresponds to the number of vertices of the final diagram, okay? So this is for the double line graph, double line diagram, and this is for the triangulation in this case. Okay. Now, remember that the counting that we were having, let me just check 1 second that I get everything right here. So I get here E minus V minus H, but this corresponds to GS2. Number of edges is the same. Now number of vertices goes to number of faces, and number of closed loops goes to the number of vertices. So now I can use Euler's formula for closed Riemann surface. So Riemann surface without boundaries, closed Riemann surface, which is probably the Euler formula that you are more familiar with. And this is a very nice formula which tells me that the number of edges minus number of faces minus the number of vertices is 2G minus 2. And for those of you who are familiar with homology, you know, this is the 1 homology, number of edges. This is the 2 homology. And this is the 0 homology. So this is actually minus the Euler characteristic of the Riemann surface. Okay, so that's how you can actually interpret double-line diagrams as closed Riemann surface with no boundaries. Okay, and you know it's useful to have both interpretations. One, of course, having closed Riemann surface is very nice. Having Riemann surface with boundaries is also useful because if you remember the powers of the top parameter. So when we're introducing this top parameter here, and the powers of the top parameter were t to the h. So the number of boundary loops appears explicitly as the power of t. So sometimes it's also useful to have this picture in which you have Riemann surface with boundaries, and the power of t is the number of boundaries. What is interesting is that the genus of the Riemann surface that is associated to these diagrams is the same in both interpretations. Okay, so that's useful and important. So remember that this was interpreted as this thing here was interpreted as a Riemann surface with 3 boundaries in the open Riemann surface interpretation, in the interpretation of Riemann surface with boundaries, a sphere with holes. And in this closed Riemann surface interpretation is still a sphere. And the same thing goes for this diagram. In our previous interpretation of Riemann surface with boundaries, this was a torus. So remember here, let me actually now, I changed this drawing, so this is now a torus, okay? So this was a torus with g equal 1 and h equal 1. So this was a torus with a hole in the previous interpretation, and now it's simply a torus with no holes. And you can see, for example, that this h equal 1 corresponds to the fact that this triangulation of the torus has a single vertex. Okay, actually, you think about this, you have something like this, and this is the single vertex of the torus. Okay, so the single vertex of the torus corresponds to the single line of the double line diagram. But this is still a torus. So before it was a torus with 1 hole, now it's a torus with no holes and 1 vertex. So this is how these things, this is how these work. As I said, these are 2 useful interpretations of diagrams that you can make based on Riemann surface. Okay, so essentially, depending on your taste, you can use one interpretation or the other. Okay. So I think that finishes more or less the discussion on Riemann surface and the correspondence to double line diagram. So I think this is something interesting that you probably haven't seen in your previous course on random matrices, is that if you have a theory of random matrix, you have a way of generating Riemann surfaces out of the diagrams. Okay, and this has been extremely important for many reasons. Okay, and this is something that people doing traditional random matrix theory do not really take into account. Actually, you can use quantum field theory techniques to enumerate discretized Riemann surface. I really recommend you very strongly a very beautiful article. I think you can find it in the references of the Polycopier, which is by Bessis, Tixon, and Zuber, which is called something like I think it's something like quantum field theory techniques in enumeration or something like that. No, I didn't refer to this. So something like QF theory techniques in the enumeration of graph or something like that. So this is a very, very beautiful article, which is makes manifest that you know, you can use these ideas of quantum. I mean, after all, our way of approaching the matrix models was quantum field theory approach, in which we thought about these matrix models as perturbations of a Gaussian theory, and this leads automatically to a theory of Feynman diagrams. And these Feynman diagrams can be interpreted in terms of Riemann surface, discretized Riemann surface, and eventually you can use this quantum field theory approach to make contact with the enumeration of discretized surface. And this has been an enormously important connection in combinatorics and so on. Okay? Okay, very good. So are there any questions so far? Any questions, comments?
Yes, so here I have one question.
Yes.
So in this, when you have such a, let's say, the triangulation.
Yes.
Then for a given surface, there are different triangulations. They are all related by this flip move, where you slide the diagonal of a square.
Yes.
Does this correspond to something in the numerator, like in the QFT, or?
That's a good question. So what is this move in which you flip the orientation of the triangle, right? Or something?
No,
like
so if you have a square and
yes.
You have one of the diagonals, you change it to the other diagonal.
Yeah, this one, right? Oh, sorry.
Yeah. I know what you.
Yeah.
Mm-hmm. Or
Oh, I think these two are counted just once by this procedure because they correspond both to this. I think this corresponds to two different orientations of the graph. I think they are completely equivalent from the point of view of this quantum field theory construction. Yes, I would say so.
Okay.
Yeah, because you see, this is like doing this, and this is like doing this. So from the point of view of the graph, they are equivalent, right? I mean, the quantum field theory doesn't distinguish how you put the graph in the space, right? So.
But still, like those two things you drew, like they can be connected to other things too. So is it always true that it's diffeomorphic?
Yeah, I think so. I think so.
Okay.
I wouldn't. I haven't gone through the details, but I think this is just in this kind of flip, which from the point of view of the Feynman diagram is completely equivalent. So there is no overcounting of this operation, I would say.
Okay. That's probably somehow related to the mapping class group. I don't know.
Yeah. If you do all the details of these quantum field techniques, you eventually associate to each discretized Riemann surface the inverse of the automorphism group, of the order of the automorphism group of the line diagram, which corresponds to the kind of standard counting in the discretized Riemann surface. So essentially, the quantum field theory techniques give you the standard counting. So I think I'm probably including also this sort of identification.
Okay, thank you.
Okay, more questions, comments? Okay, so now I'm going to really change subject. So maybe I can even use a different page. So this first chapter was an introduction to, was really like a trivial thing in the sense of using quantum field theory in 0 dimensions. So this is a topological theory almost by construction. But if you want to really go to higher dimensions, you have to do something else to have a topological field theory. And just as a general story, traditionally there have been two types of topological field theories, which are sometimes called Schwarz type and Witten type. Now, Schwarz type topological field theories are theories in which the action that defines the theory is itself topological, doesn't depend on the metric to start with. And the most famous example of this is Chern-Simons theory, for those of you who have maybe heard these words. And these are, and we could do the course on Chern-Simons theory, but this is a relatively complicated quantum field theory. Now, Witten type theories are much more subtle because these are theories in which you have a dependence on the metric in principle. When you start defining things depends on the metric. But there is a symmetry in the theory which essentially gets rid of this dependence. And this symmetry is a version of what is called supersymmetry. So in order to, in these theories, essentially you use supersymmetry or some version of supersymmetry to get rid of the metric. So I would like to actually introduce, I will actually focus on this course on Witten type theories. So in order to do this, I have to explain a little bit what is supersymmetry. And of course, supersymmetry is a complicated thing with many implications. So I want to start with kind of very elementary things. So the chapter 2 of this course is going to be supersymmetric quantum field theories in 0 dimensions. So we are going to start in, we are going to continue being in 0 dimensions. Because it's where life is simple, where we are just actually dealing with functions, but we are going to introduce a new ingredient, which is here supersymmetry. Okay. Now, in order to introduce supersymmetry, we have to introduce a very interesting object, which is Grassman variable. So my first topic here is going to be the introduction of Grassman variables. Now, Grassman variables is an infinite subject. You can spend a whole year studying Grassman variables, but actually this is not something that physicists do. Physicists have like a very down-to-earth approach to Grassman variables, and this is in a sense what I'm going to try to do. I'm not going to spend too much time working with, I mean, the important thing is that you actually learn how to work with Grassman variables. There are many mathematical structures behind Grassman variables, but as I said, I think it's really better to have like a more kind of practical point of view, which is what physicists usually do. Actually, if you look at the books, the quantum field theory books, where Grassman variables are usually introduced, it's always a kind of very down-to-earth approach. But if you want to have like a more mathematical approach, I can only recommend you the book by Tector, which is called Quantum Mechanics for Mathematicians. This is an really excellent book. I cannot praise it enough. And this book has a very, very beautiful chapter on Grassman variables. Okay, so what are Grassman variables? Well, Grassman variables are anti-commuting variables, are variables which anti-commute. And this is the most important thing. So you have like two Grassman variables which are going to denote by the letter theta. They have the property that if you reverse the order in which they multiply them, you get a minus sign. Okay, so this is, if you want, different from what are commuting variables, in which you essentially the multiplication is commutative. Here the multiplication is anti-commutative. Okay. Now let me make a formal definition for those of you who are more formal, so you are relaxed. So the definition of a Grassman algebra. So a Grassman algebra with n generators, which I'm going to denote by GRN, is a C algebra. It's an algebra over the complex numbers, where the generators, which I'm going to denote by, by these letters like theta 1, theta 2, ... theta n, satisfy that theta I, theta j, and introduce here this anti-bracket is equal to 0 for ej from 1 to n. And I remind you that this anti-commuting bracket is just AB plus BA. Okay? So this bracket means just that Ti Tj plus Tj Ti is equal to 0. Okay? And in particular, Ti squared is equal to 0. So these are nilpotent variables, okay? So this is what a Grassman algebra is. Okay? And the idea is that we have introduced quantum field theories based on variables. These are what are zero-dimensional quantum field theories, and now we're going to try to extend them by using the Grassman algebra. But this will take us some time. So let me mention some facts about these Grassman algebras. So this is a polynomial. So GRN is a polynomial algebra. So essentially, its ingredients are polynomials in these variables theta with complex coefficient. Okay. So essentially, any element in the algebra, which I'm going to call f of theta. So I think about theta as a vector, or as, I mean, we have n variables, so let's think about as a vector of n variables, is going to be a sum of variables like this. So let me be more precise, like this, and then you have f equal ek, and then you have theta E1, theta ek, okay? So this is a general element of GRN. And so let me make some comments here. So these are polynomials in the thetas. Now it's clear that if you have n generators, you cannot have more than a polynomial of degree n, because any polynomial of degree n plus 1 in these variables has to be 0. And this is just because of this nilpotent property. I mean, you have more than a product of more than n generators. Some of these generators will have to be repeated. Some generator will have to appear here more than once. But then by so for example, you have theta 1, theta 3, theta 3, theta 3, theta 3, theta 4, theta 1. This is 0. And why? Well, because, you know, you can jump with theta 1. You can jump. Every time you jump, you get a -9. You can jump here, you can jump here, you can jump here. And when you get to theta 1, you will get theta 1 squared, theta 2, theta 3, theta 4. And this is 0. Okay? So any product where there are more than n different thetas is 0. Of course, you can always put the thetas in a given order. So I can put always the thetas by using the anti-commuting property. I can always order any monomial in terms of ascending, ascending indices. Okay, and this is what I wrote here. Okay, what I wrote here is that I order the index. So the I1 is the lower index and ik is the higher index, and I can always order any monomial like this. Okay, and in particular, these f's are complex numbers. So these are complex numbers. So this is what happens when you try to construct polynomials in these anti-commuting variables. First of all, there is a limit. I mean, after you get to degree n, the thing stops, and then, you know, things are ordered. And you have seen something like this before in your life, and this something that you have seen which behaves very similar to this are differential forms. Differential forms are very, very closely related to Grassman algebras, and we will actually explain this connection later on. But this is essentially what happens with differential forms. You have differential forms on a manifold of dimension n. You cannot have differential forms of degree higher than n. And you also have this anti-commuting property that, you know, the coefficients of the differential forms, you know, can be ordered in this way. Okay, so for those of you who are familiar with differential forms, which I hope is all of you, theta i's are very closely related to what you would call the xi's. Okay, and we will make this more precise later on. But so in particular, this means that the algebra that you're used to when working with differential forms, the stereo algebra is essentially the algebra of Grassman variables. Okay. Okay. Are there questions on this? I mean, we will learn to manipulate these things. Now let me make two comments on this. So the first comment is that GRN is a graded algebra, because we can associate, we can associate a degree to each element, to each monomial. Oops, sorry. So to any monomial in the thetas. So essentially, theta 1 has degree 1. Any generator has degree 1. Okay. So theta I, theta j has degree 2, and so on. And you see that here, I can decompose any element in the sum of monomials of degree k. Okay, here this has degree k. So at the end of the day, I can write this as a direct sum of k0 to n of grade, let me write it like this, n k, and grade n k are elements of degree k. Okay, so this is a decomposition you have, and sometimes, so this is a different decomposition. I'm going to write this as grade 0 n plus grade n1, and the reason is the following. So why I decompose into things? You see, when things have odd degree, they anti-commute. Okay, but since we have degree 2, they actually commute. So for example, theta 1 and theta 2 and theta 3 and theta 4 commute. So these are elements of degree 2, right? So, and this is very easy to see that theta 1, theta 2 times theta 3, theta 4 is theta 3, theta 4 times theta 1, theta 2. Okay, and the reason is that, when you move these things here, and you can move this, but you move it through an even number of theta, so you don't get any sign. So these things commute. So things which have even degree in Grassman algebra, they actually behave like commuting variables. But things which have odd degree behave like anti-commuting variables. Okay? So these are the even degrees. So this is, if you want, a GRN0 is a direct sum where key is even of things which have this degree, and GR1 are the things which have odd degree. Okay, so these are elementary decompositions that you can make here. Okay, so these are vector space decompositions of this Grassman algebra. Okay. Okay, so essentially you can play algebraically with these objects, but we want to do something more. We want to do really quantum field theory. If you want to do quantum field theory, in particular, you will have to be able to do two things. You should be able to take derivatives, and you should be able to define integrals. Okay. Remember that in a quantum field theory in 0 dimensions, the most important quantities are integrals over the appropriate space. So that's how we define this partition function or this correlation function. So if we want to make a quantum field theory in 0 dimensions with Grassman variables, we will have to be able to define an integration operation, and we will have to be able to define a differentiation operation. Okay. So this is what we have to do now. We have to define the analogs of the derivatives and integrals for these Grassman algebras. Very good. So derivatives. So let's start then by defining derivatives. Now derivatives work. We have a polynomial algebra, so it's enough to learn how to take derivatives with respect to with respect to variables of polynomials. Okay, so so the derivative with respect to ti. So you will have n derivative operators. And the way this works is very simple. So first we are going to define this on monomials, and then we are going to extend it linearly, okay, as usual. So how we define this on monomials? Well, you have the partial derivative with respect to theta I of a product of this form. We will have to, this is equal to a sum, from L equal to 1 to K, with -1 to the L minus 1. And then I'm going to write it like this. So where this means theta, theta IL means that we remove this variable. Times DELI. Okay, so we remove we remove this generator. So this is not a very clear definition. Okay, but what this says is the following: when you add with the derivative, you start scanning this monomial. You start scanning the monomial, and then you see if any of these indexes is equal to I. Okay. If the first index is equal to I, you remove it, and you have the first term, and then you continue, and every time, of course, you know, the index I only can appear here only once, because otherwise this is 0. So you have to essentially scan this to see if there is any of these indices is equal to the index I, and then you have to remove the theta I if it's there, otherwise it's 0, and then you have to put a sign which takes into account how many times you have to jump with this delta with respect to delta theta I to reach the index theta I in this monomial. Okay. Well, this was not very clear. So anyway, let me give you some examples. So let's calculate this. So what is this? Well, it's very simple. Here, theta 1 is the first thing. So you take a derivative with respect to this. You remove it, and then you get theta 2. Okay? Now, on the contrary, if you have theta 2, theta 1, you have to be careful because theta 2, theta 1 doesn't act, the derivative with respect to theta 1 doesn't act on this, so it has to jump over it, you get a number, a sign, a minus sign, and then you hit theta 1 where you remove it. So this will give you minus theta 2. And this is compatible with the fact that theta 1, theta 2 is equal to minus theta 1, theta 2, theta 1, okay? And then, you know, you can, you know, I don't know, you can compute, for example, this. This would be, well, again, you know, you have to hit theta 3, so you have to jump over theta 1, theta 2, you hit theta 3, and you remove it, and this gives me theta 1, theta 2, theta 4, okay? So this is how the Grassman derivation works. Okay? So you see, it's very similar to a standard derivation, and the only thing you have to take into account that is this fact that when the derivative jumps over the signs, over the thetas, you inherit minus signs, and this is needed. Otherwise, you know, these two results will be completely incompatible. I mean, if you want this to be, you know, to be compatible with the fact that theta 1, theta 2 is equal to minus theta 2, theta 1, you have to have this, okay? So this is how it works. As I said, you know, this is a derivative in a polynomial algebra, so, and in particular in this polynomial algebra, the only powers that you can get of the variables are 0 or 1, so, you know, the derivative is completely trivial, okay? It's like taking derivatives of linear functions, okay? And just taking into account the anti-commuting character of the variables, okay? Is this clear? Are there any questions on this? Okay, we will have the opportunity to make more derivatives of this, so that's how does it work? Okay. Okay, now derivatives are easy, and integrals are actually also very easy. Integration is one of the more difficult things in mathematics. I mean, you know, it's hard to emphasize. I mean, you cannot overemphasize the fact that, you know, most of the problems in mathematics and mathematical physics and in physics essentially, you know, come down to, you know, boil down to integrals. Okay, so integration is very hard with commuting variables, but for anti-commuting variables, integration is very easy. So integrals essentially are, for Grassman variables, the right definition of integral is something which is essentially equivalent to a derivative. Okay, so we have to define a very particular integration operation, which is called the Berezin integral, due to the name in this way in honor of the Russian mathematician who developed Grassman theory, the theory of Grassman algebras. And the Berezin integral, you know, if you have one variable, is defined by the very, so you have just one variable, is defined by two simple rules. Now, the first rule is that the integral you have to introduce also a measure, okay? So the integral of d theta is equal to 0, and the integral of d theta, so the integral of 1 is equal to 0, and the integral of theta is equal to 1. So these are the two rules of Grassman integration. So you can think about the Berezin integral as a linear functional acting on elements of the Grassman algebra, which in the case of one variable, it gives you 0 for 1 and 1 for theta. And then this in a very natural way. So let me give a definition. Okay. So Berezin integral, it's a linear functional as integration. Integration is linear. So I'm going to write it like this. It's an integral which goes from the Grassman algebra of n variables to the complex numbers. And essentially, the thing that this Berezin integral does is to keep the coefficient of the highest term in the function. So it's defined as follows. So remember, I wrote here the most general form of an element of the Grassman algebra, which was this one. Okay. Now the Berezin integral essentially looks at the highest possible number of thetas, and it removes them. And just keeps the coefficient of the highest power of thetas. So let me write it here. So imagine that we have a general element of the Grassman algebra. So remember that this element will have many terms, but then there will be the term of the highest degree, the term which has degree n. And term which has degree n can be always written as f1 to n, so a single coefficient, times theta 1, theta n. You see, maybe I should make a comment here, is that the number of so if you think about GR and K as a vector space, the dimension of this is n over K. Okay, because this is the number of. So you can think about this in this way. So the element of degree is K. You have to choose K indexes in n, and the ordering is in essential. So this is essentially n over K. So here, when you have the highest possible degree, in particular dimension of GRN, n is just 1. And so this means that here there is a single coefficient. And from all the terms in a general function of the Grassman algebras, the Berezin integral just keeps the higher power, f1 to n. So this is the definition of the Berezin integral. You see, it's the higher n generalization of what happens when you have just one single variable. Okay? So is this clear? Is this clear how this Berezin integral works? So this is a definition. This definition was motivated by various constructions in quantum field theory. But you know, we're just taking it as a definition of integral. Okay. Is this clear? So you see, that's what I said, that, you know, integration with anti-commuting variables is very simple, because, you know, it essentially just picking one term in the polynomial. So it's really trivial. The life would be much easier if all the variables were anti-commuting. Okay, so notation, a notational point. I'm going to write d theta as the measure of this integral. So the kind of things that we want to compute then are things like this. Okay, and this is, as I said, f1 to n. So the highest power of the term, the coefficient of the highest power of the thetas in f of theta. Okay. Okay, now it's 10, and I think we should still be able to make a pause. So in order to make a pause, I guess I will stop the recording, and I don't know if there is any way of maybe, I don't know if I can stop the video so that you cannot play Big Brother with my home, because I'm at home, as you can imagine. So,
below in the toolbar, there should be the option, I think.
Sorry?
In the toolbar below, there should be the option to stop recording.
Yeah, stop recording is easy. Pause recording is easy. Okay. So let's go back to work. So we were discussing Grassman integration. So that's the definition. A useful formula, which we will use a lot of many times, is the following. As I said, the only thing that we have to really care when we look at when we do a Berezin integral is to take into account the maximal number of thetas, that the terms with the maximal number of thetas. So at the end of the day, the only thing that you really need in order to do the Berezin integral is a formula for a sequence of n thetas, but in any order. That could be in any order. So since we are sophisticated mathematicians, we are going to denote an arbitrary order by a permutation. So sigma is an element of the permutation group of n elements. So this means that this is not necessarily in the right order. So this could be any permutation of the labels 1 to n. And the Berezin integral tells me that the integral of the thetas when they are in the standard sequence, theta 1, theta 2, up to theta n, is 1. Now, if I have a sequence of thetas which are not in the right order, I have to make a permutation to put them in the right order, and then I will have to swap the thetas. And every time I do this, every time I swap two thetas, I will get a minus sign. So when I put these thetas back into order, what I will get is a minus sign or a plus sign. So it's actually minus 1 to the signature of the permutation theta. Okay, remember that the signature of the permutation theta, sorry, not theta, sigma. The signature of the permutation sigma is the number of transpositions that I have to make in order to put this sequence of sigmas in the standard sequence 1 to n. Okay? The number of transpositions that take me from 1n to sigma 1 up to sigma n. And precisely since each transposition corresponds to a swap of two thetas, this is exactly the sign I get here. So this formula, it's very simple, but it's very useful, and this will be essentially the only non-trivial formula that you need in order to do actual calculations of Berezin integrals. Okay, very good. So now what do you want to do when you have integration? So what are the things that you need in order to do integrals? Well, of course, there are many things that you want to do, but there is one particular thing which is very useful, which is a formula for the change of variables. Okay, so when we do integrals, we want to know what happens when we change variables, and another thing that you want to do is Gaussian integrals. Okay, and that's precisely because we have seen that Gaussian integration is very important in the context of quantum field theory. So we would like to understand what happens with Gaussian integration for Grassman variables. So these are the two things that we are going to do now in the context of Grassman integrals. So we are going to first address the question of what happens when we change variables, and we are going to see what happens when we do Gaussian integrals. So let's first do the change of variables. So we are going to consider linear change of variables. So we are going to consider a linear change of variables. Which I write in this form. So let's suppose that I do the change of variables. And then, you know, I have this lemma, very simple lemma, which says that the integral d theta f of theta is equal to, sorry, let me just point out, this is linear and invertible, okay? So the formula I have for the change of variables is this one. So just to understand the notation, so d theta twiddle is the measure for the theta twiddle variables, and f twiddle of theta twiddle, or actually the other way around. Sorry. Okay, so it's just the function. It's just the same function, but re-expressed in terms of the theta twiddles. Okay. So let me make this slightly clearer. So this is, I have to put two hats on the variables. I have the twiddle hat and the arrow hat. That's why it's a little bit complicated to write this. So this is the formula for the change of variables. And notice that this has the opposite factor of the determinant that you would have in a bosonic change of variables. Sorry, in a bosonic. So I'm already talking like a physicist. You have commuting variables and you make a linear change of variables, you will have the determinant in the numerator, not in the denominator. And this is one of the things that makes Grassman variables to behave in a sense oppositely to commuting variables. Now, this is very, very easy to solve, okay? And the reason is this following. So remember that from f theta, the only thing that we have to change, so f theta will have various terms, and then here we will have the term which is relevant for the integration, which is this one, okay? Okay, so this is the thing that we have to worry about. Now, we are going to make this linear change of variables, okay? So if I make the linear change of variables directly here, what I will get is the following. I get f1 to up to n, and then, you know, each of these theta ones is going to be a linear combination of the theta twiddle, okay? So I will have something like that here. I will have I1, In from 1 to n, and then I will have here A1, I1, AN, IN, and then I will have here theta twiddle I1, theta twiddle IN. Okay. So this is just the last term. So of course there will be, sorry. Oh boy. Okay. So I have other terms here, but this is the term I will have to focus on. Now notice that after change, even even if I change variables, the only relevant term in this function is the term which involves the highest the possible number of thetas. Okay, the other terms in f, when integrated, won't give me any difference. Okay, won't give me any contribution. Now, let me just manipulate this a little bit. Now, notice something here. Notice that, again, I can always put these thetas. Now, I have n theta twiddles here, but they are not ordered. Okay? So actually, if you want I1 up to In, I have to look at these indexes as a permutation of the original index 1 to n. So I actually have here, if I order this, what I will get is the following. Notice this. Notice this formula, which is so. Let me write I1 In, the indexes I1 In, as a permutation of the index sigma 1. So I associate any of these indexes to a permutation. So if I sum over all possible indexes, I'm summing actually over all possible permutations. And now I order these indexes. So when I put them in the right order, I will get -1 to the epsilon sigma. And then I will get here A1 sigma 1, A1 sigma n, this times theta 1, theta n. Okay, so this is what I get. So this means that f theta, when written in terms of these variables, is f1n. So what is this? What is this thing here in the parentheses? Well, this is just the determinant of A, the determinant of the matrix A. Okay. So remember that this is f twiddle of theta twiddle 1, theta twiddle n. Now, in particular, we deduce from here the following formula. The upper component of f twiddle, so the most, the coefficient of the highest, of the largest monomial in thetas in f twiddle is just f1 to n times the determinant of A. So this is just what I obtain by changing variables in the function f. Okay. And now we're almost done, because what is this? Well, this is by definition f1 to n. And this is 1 over the determinant of A times f1 to n, because we just derive this result. But this is precisely 1 over the determinant of A times the integral of the theta twiddle times f twiddle theta twiddle. Okay. I mean, by definition of Grassman integrals, this integral is the highest coefficient in f twiddle. Okay, so the formula is established. Okay. So you see that Grassman integration has a simple change of variables formula, and we can actually summarize this by saying that by writing this sort of heuristically, we can think about this formula as expressing a change of variables like this way, okay? Which is exactly the opposite that you would find in commuting variables, okay? And this is because the reason why we get the opposite to what we would get in standard bosonic variables is because the Beresing integral, the integration over Grassman variables, is just the opposite. Is actually acts like a derivation. So it's, integration with Grassman variables is like taking derivatives, and that's why many of the properties of the Beresing integral are more like properties of derivatives than properties of integrals. Okay? Very good. Are there any questions on this? Okay, as you see, working with Grassman integrals involves working a lot with determinants and antisymmetric objects. And this is because of the anti-commuting nature of these variables. Okay, very good. So now Gaussian integrals. So one of the so in order to motivate why we want to do Gaussian integrals, I mean, of course, it's a nice exercise in Gaussian in Grassman integration, but why do we want to do Grassman integrals? Well, Gaussian integrals. Well, the reason why we want to do Gaussian integrals is the reason actually, you know, as far as I know, the only real use of Grassman variables in life is actually to introduce and to actually deal with what are called fermionic degrees of freedom in quantum field theory. And eventually, what you have to do, if you are familiar with this path integral formulation of quantum theory, what you want to do is to give a path integral formulation of fermions, and this means that you will have to write a similar object to what you write for commuting variables, but for anti-commuting variables. And as we have seen in quantum theory, Gaussian integrals are very important because they are the starting point of an interacting theory. So usually when we have a theory, a complicated theory defined by a complicated integral, we try to think about this theory as a sort of perturbation of a Gaussian integration. Okay, and that's what we are going to try to do here now. So we're going to use Gaussian integrals for Grassman variables because this is the generalization, the natural generalization of Gaussian integration for commuting variables, which play a fundamental role in quantum theory. Okay, very good. So, okay, so Gaussian integrals. So we are going to assume now that n is the number of Grassman variables. We're going to assume that this number is even. Okay. So this is needed for Gaussian integrals to be non-trivial. Okay. And you know, a Gaussian integral is the integral of an exponential of a bilinear, of a quadratic form in variables. So when we deal with commuting variables, you have something like this. So I'm assuming that the repeated indices are summed over, so this is Einstein's convention. So this is the kind of integral you want to do. Now, for anti-commuting variables, our integral will be of the form θ1, θn, so it's a Berezin integral. And now I'm going to do an exponential, and I'm going to use again a quadratic form. So let me, for the moment, introduce the explicit sum symbol, and I will have aij, θi, θj. So I want to do this integration. So this is a Gaussian integral in Grassman variables. Okay. Well, apparently you are not seeing this because this is now taking some time. I hope it's going to work. Well, for some reason, the sharing of my screen is not working properly. So maybe I'm going to stop it and do it again. Just 1 second. Okay, now here we are. Sorry, but unfortunately my cable doesn't work for the Zoom for the sharing. So I have to do this in this way, which is probably much less efficient. But I haven't been able to make it work with the cable. Okay, so this is a Gaussian integral. Now, Gaussian integrals for Grassman variables, again, are very different from Gaussian integrals for commuting variables. They are really very different. You see, this is an actual integral. You know, the x variables can go to infinity, and then, you know, you have to integrate the Gaussian. It's a non-trivial integral. You know, the integration of the Gaussian is not an elementary integral. You have to think about how you do this integral and so on. Now, this integral, it's completely combinatorial. I mean, the only thing you have to do is to expand the exponential and pick the highest power of the thetas, okay? So let's actually expand this exponential. So this exponential can be expanded, you know. It's, that's the definition of the exponential. So this is the sum from k equals 0. Let me just 1 over 2 to the k, 1 over k factorial, and then I have this thing, ij1 to n, aij, theta I, theta j to the k. So, you know, you just take powers of this. But again, one very beautiful property of Grassman variables is that the exponential truncates. And why is this so? Well, you see, here we have n variables in total. So we know that products of more than n variables are 0 by definition, by the anti-commuting character of the Grassman variables. So here we have 2 variables. Now, when k is equal to half of n, which is m, this is the last time we will have all variables. This is the last time that we will have, oops, what is going on here? Sorry. Oh. Okay, sorry about this. So the maximum, the last term that will contribute here is the term which will have n variables, but n is twice m. So the last term that will contribute here is m. And k m plus 1, there will be here n plus 2 variables. So it's clearly that it's going to be 0. Okay, this is the last term that I want to appear here. So again, that's a beautiful property of exponentials of Grassman variables. They truncate. They are not infinite series, but just polynomials. Okay? Everything here is a polynomial in Grassman. In Grassman variables, everything reduces to a polynomial, to a calculation with polynomial. Okay. So this is this is an exact formula for this exponential. But now we want to do an integral. So this integral has to pick just the term with all the thetas, okay? And it's clear that it's only the last term that will contribute. So from all these terms, only the last one, so the one from k, for which k is equal to n, will contribute. So the term that will contribute is this one to the integration. So we can just look at this term. Okay, all the terms where k is smaller than n will not give me enough thetas for the integral. There will be less than n thetas in these terms. So the integration of Grassman over the Beresing integral will just take them to 0. Okay, we just need the term with the maximum number of thetas, and this is just this. Okay. Okay. So now we just expand this. Okay, and you see that here you will have m indices from 1 to n. You will have m indices for j, 1 to n. So I can write this as a11, j1, aim, jm, and then theta I1, theta j1, dot 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 theta am theta jm. Okay, so this is what you get from this expansion. And again, we use our principle. Our principle is that this has here there are two n, here there are two m, so n thetas, and we are going to integrate this. So again, the way we proceed this as before, we're going to think about I1, J1, Im, Jm as a permutation. So these indices, we are going to think about them as a permutation of the n indexes that we have here, sigma 1, sigma 2, sigma n minus 1, sigma n. Okay? And all these sums, we will be able to write them as permutations here. So this gives me 1, 2m, n factorial, and then I will have here permutation Cn of A sigma 1, sigma 2, A sigma n minus 1, sigma n, and then I have here C theta 1, theta n. Oops, sorry. And then we will have to integrate this thing, but we know what is the integral of this. Okay, the Beresing integral of this is minus 1 to the e sigma. Okay, where the epsilon of sigma is the signature of the permutation sigma. So we have our final formula, which is that the integral, the Gaussian integral of this sorry, let me write this in a nicer way. Back 1/2 of sigma ij1 n iij theta I theta j is equal to 1 over 2 to the m factorial sigma sum over permutations of this with this sign. Okay. And so sorry, let me mention something which I forgot to say, is that without any restriction, I can always assume that this matrix is antisymmetric. And the reason is that you have an object with two indices multiplying something which is manifestly antisymmetric. Only the antisymmetric matrix A survives. So this A, it's are the indices of antisymmetric matrix. Okay. And as I said, this is not a restriction, because if this two object, this matrix was not antisymmetric, after taking the product with times theta I theta j, it would project into the antisymmetric part. You know, any matrix can be divided, can be written as a sum of a symmetric matrix plus an antisymmetric matrix. It's clear that the symmetric part of this matrix times theta I theta j would be 0 automatically. So only the antisymmetric part survives. So I'm going to now assume that this matrix is antisymmetric, and this is without, this doesn't imply any restriction. Any integration of this will only be sensitive to the antisymmetric part of A. So we get this formula here, and this is the formula for this thing. We have discovered a new object. So what, I mean, this is not the determinant of A. It's a slightly different object. When you have a new object, it's like when you have a new child, you baptize it, and we are going to call this the Pfaffian of the matrix A. Okay, this is the Pfaffian. So we give a name to this object, it's called the Pfaffian. And it's the Pfaffian of the antisymmetric matrix A. So it's the Pfaffian is an object which appears naturally when you do Grassman integrals of Gaussian functions. Okay. So let me give an example to see what it is, because it's good to understand what kind of object is this. So the simplest case is when n is equal to 2. So A is an antisymmetric matrix of the form 0, A minus A0. So this is the simplest case. So if n is equal to 2, m is equal to 1, and then, you know, what is this? What is the Pfaffian of this matrix? Well, it's 1 over 2. So 2 to the 1 is 2, 1 factorial is 1, 1 over 2, and then I have to sum over permutations of two indices. There are two permutations of two indices, and, you know, the permutations of sigma 2, there is one which is the identity, and there is another one which is just the elementary transposition. So this, if you apply just the formula here, the first integral, the first sum is A12, and then I have the signature of the identity, signature of this one, the signature of the transposition is -1, so there's actually a -9 here. Minus A21, and of course this is A. So the Pfaffian of the matrix is A. As I said, it's not the determinant, okay? Because the determinant of this matrix is A squared. So the Pfaffian is actually some sort of a square root of the determinant. Okay? It's actually possible to show, and you will do this in the exercise session, it's actually possible to show that the square of the Pfaffian is the determinant of the matrix. So this is a general fact of life. Of course, in this example, it's true, but it's actually more generally true. It's a general property of the Pfaffian. So the Pfaffian of an antisymmetric matrix is, in a sense, the square root of this determinant. And as I said, it's really a natural thing coming from Grassman variables. Okay. Very good. So we have learned Grassman variables. We have learned how to take derivatives. We have learned how to do integrals. We have learned how to do Gaussian integrals. And now we are going to pass to the final step, which is introducing super functions. Okay. So before introducing, yes.
Just a question. What changes when the number of generators is odd in this Gaussian integration?
Well, if you have an odd number of generators, this type of integrals just gives you 0. Okay.
Okay, I see.
Because, you know, the power that you get when I do this, when I do the exponential of this, you see, I always get an even number of thetas, right?
Yes. Yes.
So, you know, this formula is, you know, if you look at this formula, this formula is always true, right? This formula is always true.
Mm-hmm.
Now, if n is not even, okay, here you will have to truncate the thing, but it's at the, you know, here m is probably the integer part of n over 2 or something like that. If n is not even, but you see the number of thetas that appear here is always even, because it's always an even number of thetas to some power. So there are always 2k variables here. But if n is not even, there will never be a term in the expansion of the exponential which will give you the maximal number of thetas, because the maximum number of thetas is odd, and the terms that you get from here are always even. Okay, so if n is not even, Gaussian integrals of this type are trivially 0. Okay,
I see. So when you take the large n limit with these Grassman variables, you have to keep in mind that it's only for even n.
Well, you don't. Right now, we don't want to take a large n limit of these things. But if you wanted to do this, yes. I mean, you know, there will be some sort of parity property, yes. But you know, this is just a kind of simple thing that if I have an even number of Grassman variables, sorry, an odd number of Grassman variables, then Gaussian integrals just give you 0. Okay. Now, actually, as you will see also in the exercise, the most common situation is in which you have like complex Grassman variables, and then they come in pairs. So that's in a sense the most typical situation in quantum theory. But again, you know, you also can have these real Grassman variables in which you know, you can have odd or even numbers. And this is not trivial. I mean, the fact that Grassman variables with an odd number have some sort of a special properties is really a pervasive factor of Grassman theory. I mean, this is behind many properties of, for example, supersymmetry in odd dimensions is very different from supersymmetry in even dimensions, and this, in a sense, goes back to this fact. Okay.
Okay.
But technically, it's just that if n is not even, then Gaussian integrals are trivial, are always zero. Okay. But thanks for the question, because otherwise it sounds like very strange that I restrict to an even number of variables.
Yeah, thank you.
Are there any other questions? Okay, so now we're going to introduce super functions, and this sounds very fancy, but it's just an elementary thing what we're going to do. Now, so far, we have considered Grassman variables. So we have considered an algebra, okay, in which you have f of theta, and then well, let me repeat my. Okay, sorry. So I think this was one, and then I have to have here a sum over. So we have here something like 1, I1, blah, blah, IN, and then F, I1, IK, and then theta I, theta IK, okay? And here, these F's were, these F's were complex numbers, okay? So this is a function of the thetas, but the coefficients themselves are not functions of anything else. They are just constant numbers. But you don't have to have a lot of imagination to think that it's very easy to generalize this if on top of the theta variables, you have commuting variables. So let's now assume that we have commuting variables, x1, x, I don't know, p, are commuting variables. So you can think about this as variables in, say, real variables in Rp. So let's not, for the moment, do anything fancy. And on top of that, we would have anti-commuting variables. So we have P commuting variables and N anti-commuting variables, right? This is perfectly natural. So if we have both commuting and anti-commuting variables, then it's very natural that now I promote this polynomial in the thetas, where the coefficients were just constant numbers, to polynomials in the thetas, where the coefficients are complex valued functions of the commuting variables x, right? And that would be something that it should occur to you naturally, right? So I'm going to promote this then to something slightly more general, and I'm going to introduce a function of x. So x is this, of x and theta. And then this means that these coefficients are functions of x. Okay. So they are no longer coefficients, constant coefficients, but they are functions from Rp to C. Okay. And such an object is called a super function. So remember that when you have anti-commuting variables, the most complicated dependence you can have are polynomials, okay, of this type. But of course, if you now introduce commuting variables, you can have arbitrary complicated dependence, but this dependence is going to be encoded in these coefficients, and then you still will have polynomials in the thetas. So this is the most complicated object that you can have, and it's called a superfunction. Okay. Very good. So so now once you have superfunctions, so actually you can think about this as defining, you know, manifolds are defined essentially by the type of functions that you can have. So you can go on and define supermanifolds. But you know, the kind of if you have commuting variables in RP and these anti-commuting variables θ1 to θn, you talk sometimes about the supermanifold RP bar n. Okay, so what is RPn? Well, RPn means that you have p commuting variables and n anti-commuting variables, and you define functions on this superspace. So this is what is called sometimes a superspace or a supermanifold. You know, what is a space is a space is more essentially defined by the type of functions that you can define on it. So the superspace RPn is defined by the fact that superfunctions on this space, functions on this space are these type of superfunctions. Okay, so there is a whole theory of supermanifolds, which is you know, superficially complicated. But I don't want to enter into all this game of supermanifolds, because I mean, essentially complicates things too much, and I don't think it's really worth to enter into the whole theory of supermanifolds. Essentially, for us, a supermanifold, the supermanifold RPn means that you have p commuting variables and n anti-commuting variables, and then you define superfunctions in this way. If you have a supermanifold, this means that locally you have a space which locally looks like RPn. So locally on patches you can define functions in this way. Okay, so the notion of supermanifold is simply that, you know, you will have local trivializations. On each local trivialization you will have commuting and anti-commuting variables, and you will have locally on these patches you will have super functions of the commuting and anti-commuting variables. Okay, now we will extend this. We'll come back to this next week, and we'll develop a little bit more this notion of superfunctions, and then we will be ready to actually introduce supersymmetry. Okay, so let's stop now. Do you have any questions on this?
This is Jan. I have one question.
Yes.
So here you introduce this Gaussian integral.
Yes.
And it should be used to do in some way the path integral.
Yes.
But the path integral, it should be seen as sum over all histories, and it's an integral because the histories are continuous or something.
Well,
and here,
yes.
And this Gaussian integral, like, it is defined somehow, but it's not clear that it's sum over anything.
No, but you see, here what I'm doing is not yet what I have defined is not an analog of the path integral. It's an analog of the conventional integral.
Yeah, okay, but then this analog will be used to do path integral, right?
Yeah, this can be used to do path integrals. Absolutely. Yeah.
But what is the physical meaning of the Gaussian integral? Why does it give the correct answer, like the probability or something? Or the amplitude?
Yeah. No. This is a very good question. Now, that's actually, you know, that's actually the way that you would. If I had to motivate this more, that would be in a way what I would do. But essentially, what happens is the following: the path integral is a procedure to reconstruct an object that you can define independently, which is the propagator. Okay, the propagator is an object which, in quantum field theory, in quantum mechanics, you don't have even to do quantum field theory. In quantum mechanics, you can define the propagator by just using standard Hamiltonian techniques. The path integral is a particular representation of the propagator. Okay. Now, if I do quantum mechanics with Grassman variables, I will have an analog of the propagator. Okay, and then you can see that the Berezin integral is the right definition of integration, which when you do the path integral construction, reproduces the right propagator. Okay. Okay,
that's very interesting. Thanks.
Okay, so and I don't know if I will have the time to do this. Right now, I'm working in 0 dimensions. Now, eventually, we will go to 1 dimension, to quantum mechanics, and we'll develop the theory there. I'm still not sure how much I want to say about. Sorry, this keeps coming to my screen, but anyway, now we don't need it. So if we wanted to do quantum mechanics of Grassman variables and develop the path integral formulation, which as I said, I don't know if I'm going to do this, but if you wanted to do this, this is exactly what would happen. We would construct the propagator for Grassman variables using a path integral generalization of the Beresheim integral, and you will see that it gives you the right answers. And again, if you want to learn about this, I think the best presentation of this subject is the book by Takhtayan. The book by Takhtayan has a very beautiful chapter on quantum mechanics of anti-commuting variables, where this is done in actual detail. Okay? But this is exactly, that's a very good question, Jan. Thanks a lot, because this is why the Beresheim integral was introduced in this way. I mean, I mentioned this before, that the main motivation to define this integral is because in quantum theory, you want to have a definition of integration which reproduces everything you need in quantum theory. And this is precisely the reason why Beresheim integrals are defined in this way. And you're absolutely right that, you know, if we didn't have this motivation, it's very strange why I do this definition of integration, right? Why we define an integral, which is essentially almost like a total derivative, right? It's the maximal derivative, is not the inverse of a derivative, is a derivative. So why is this the right definition? And the reason is that eventually this gives the right propagator in quantum theory. Absolutely.
Thanks.
Okay, for those of you who are not familiar with path integrals and so on, I mean, yeah, maybe you are not understanding everything I'm saying, but I hope you don't mind.
But Anton did many path integrals last term, so at least masterclass students should have seen them.
Did he do a path integral formulation of quantum mechanics in the course? So did he actually do the path integral?
I think he did.
Okay.
Masterclass students, do you agree?
I don't know. So are there any masterclass students still online? Did Anton did the path integral formulation of quantum mechanics?
Yeah, he did.
Ah, okay, very good. Okay, then there is no problem. Then that's great. Then you should.
But not everyone took the masterclass. Then again, I think.
Yeah, okay, very good, very good. Okay, so you will have now 1 hour of exercise. I'm preparing the second sheet of exercise, so I will discuss it with Tomas, and I will put it in Moodle soon. Okay. Okay, very good. Have a.
So I sent everyone the link to the exercise Zoom meeting. It's going to be a different meeting. The link should work every week, so just keep it, save it somewhere, and maybe we start in 10 minutes or something.
Very good. Okay. See you guys. Bye.
Thanks, Marcos. Bye.